9:30แล้วกัน Okay, so welcome to the third lectures, and today we're going to be discussing about the techno-economics of solar fuels. What does it mean? Meaning that we want to know uh, the economic factors that enabling the solar fuels deployment and to see how far we are from getting there from here. I remember 5 years ago when I started my research in this topic, my previous supervisor, he told me that it would take about 10 years to get it to commercialize. And I asked him again last month, and he said it would take another 10 years. So, it takes time, all these things. Let's hide this. Okay, so we talk about the X factor, and the second class we talk about fuels, and today we're going to be continuing on that, and then also assigning the group assignment. Since we are only two today, you will have an opportunity to choose first, I guess. And then, yeah, next week we will talk about the solar to green chemical and case study, and then solar thermal. Anyway, I would like to start my class with this chart. I mean, with this news. It was just a few weeks ago in Korea that there was a big fire at the government data center. And this is because of some of the lithium-ion battery caught fire. And you see this happen all the time on the airplane, in the data center. And this it's because lithium is very active. It's a very good energy storage material. It stay in our phone and everywhere, but in terms of tolerance to thermal, it is very bad. Meaning that if you trigger something, it spark a little bit of fire, it's just gonna rapidly uh explode and spread. So this is devastating news in Korea. I don't think people die because its data center is no one there, but you can see here that the 858 terabyte of government data is probably permanently lost because they didn't have the backup, and that's people's data. So we don't want that to happen, but we still need energy storage. So that's why we talk about this conversion of one form of energy to another, or more stable chemicals form rather than, maybe batteries that are easy to catch fire and also very heavy and large. Okay, so last time we talked about the calculation of solar to fuels energy, and I would like to give a bit of more context here. You can see here that the efficiency is calculated very easily from the output of energy as a fuels. Let's say you create hydrogen, then you calculate the total energy of hydrogen you produce, divided by the energy of the incident light. I'm not sure Professor Paravi has taught about the efficiency of solar cells calculation or not, but I think it's pretty similar. So that's it. The difficult thing is to understand each parameters and how to convert the unit and just have to practice. So you can see here that the energy output is really simply the reaction rate of the product you produce times delta G, the heating value, the energy value of the product you produce, right? And that would give in the unit of like joule per second or watt. So you have the watt unit on the top, and then the bottom part you have the power of the light. So normally we test or we use one sun irradiation. One sun mean we just use 100 milliwatt per centimeter. That's the normally the standard condition, mimicking the solar irradiation times by the area of your device or your machine or your like the receiver, right? And then you get the watt on the bottom as well, and then you times by 100. So that's basically the formula. So I think it's better to let you try. You can use ChatGPT or whatever. But yeah, there's two practice here. So please try maybe 5-10 minutes. The first one is to calculate the solar to hydrogen. So you have to look at the production rate and then convert it into the unit of millimole per second. All right, so right now I wrote here is millimole per meter per hour. So convert that, and then yeah, you have all the data. I put delta G here of the hydrogen and also the formic acid. So you can do both at the same time if you like, and then I will give the solution. Good. Oh, meter square, you have to get rid of it. You know the size of your device is 1 centimeter square. You can just times by the size. Yeah. Mm, okay, if you just talk about converting the production rate, you want the millimole per second, right? So you have to get rid of the unit of meter square and hour. So you times 32.6 by that 1 centimeter square, but you have to change the unit to meter square first. And then you times by you times also you change the unit of the hours into second. Got the answer? How much for the first one? Uh-huh. Okay, good. And the second one? Zero point 0.36. Okay, that's the solution for the first one. So you first get the value from the irradiance. So you have 0.1 watt per centimeter after converting the unit. Then the area is 1 centimeters. Hydrogen production rate is 32.6 millimole per meter per hour. And then chemical energy per mole of hydrogen is 237,000 joule per mole. And then the first step would be to convert the hydrogen production rate from the rate that is reported here into the unit of the formula, which is millimole per second. So converting that, yeah, you can do that easily by timing your 0.0326 with the 1 centimeters, and then also the rate, and also the converting it into the second, so you get 9.06. Whatever, that's just the conversion of the unit, and then the energy on top, you can times this number by 237,000, and then you get the watt on top. And then on the bottom, you divide it by the power of the input, and that is 0.1 watt per square centimeter times 1 square centimeters. So you get 0.1 watt. And then you divide that times 100, you get 0.215%. So that's the first one. And the second one, the answer is 3.6 because the area is 10 centimeters, and I'm not sure which part went wrong, or did I calculate it wrong? I don't know. Yeah, can you try to find where we are differ? So I did the exact same thing.
Maybe the area you convert in all the all the different all so I use long area.
What area did you use?
I use plus
Oh, 1 centimeter. So you got how much if it's 1 centimeter?
plus low like this.
I see. So yeah, we just try to calculate the solar to hydrogen and solar to fuels, and that's the solution. So if you can take photo because I don't have that on the slide. ถ่ายรูปไหมถ่ายไปแล้ว Okay. Right. Why we want to know this? Because we want to get some reference data point in order to know whether in order for us to know whether our device or our system is efficient enough to be deployed, to be economically feasible, because we're talking about the techno-economics of our device today. So that's one parameter that is very important, right? So you produce fuels, but you have to know the efficiencies. Let's say you have electricity and you want to convert into hydrogen. If the efficiency is like 30%, maybe it's feasible. If it's just 0.5%, maybe it's not. And for the photoelectrochemical device, for the solar fuels device, it is estimated that we should reach around 10 to 15%. at least in order for it to be feasible, right? So we will discuss that in the later slide. But as you can see, this is my own work. And at that time, we only get 0.2, and we want to increase from here to at least 10%. So you see, it's an order of magnitude higher that we have to improve. That's why it takes time. But there are other systems that is closer to the 10% target. Anyway, I want to point out here in the next slide that apart from the efficiencies, there is also a fundamental issues or the natures of the solar harvesting system, right? And I try to put the two different geological, what do you call, nature of the two countries. You can see here, UAE is located near the equators, and it's a desert country. And then you have the Europe that is located at a higher latitude. So you have a colder climate and less sun. So if you put this into the table now, and try to see each factor, you will see here that for the UAE and Europe, in the summer they get a lot of sun, right? UAE maybe they get 8-9 hours of sun. Europe you get maybe 12 hours of sun because the day is longer in summer. But in winter you will see that while the country located in the equator, like Thailand, for example, we get the same amount of sun regardless of the season. In Europe, you get much less. The sun would rise at 8 a.m. and would set at 3 p.m., for example. So you get much less amount of solar energy in that period of time. And as you will see from maybe Professor Paravi's lecture, that it's a difficult thing to match the demand, of the human demand, our energy demand, and the energy of the solar we can take, because as you will see later in the summer, the energy demand is lower in Europe, for example, but in the winter it's very high, but then there is no sun. So there is this mismatch that solar fuels can come into play and try to reduce this gap by, in summer when there are a lot of sun, maybe in Europe, you can convert those extra energy into fuels. And then in the winter, when you really need it, then you can use those energy that you stored. And that is called seasonal storage or long-term storage. Another point I would like to show here is in terms of space, right? If available space is also important because the country like Europe is pretty much packed because Europe continent is very dense already, and it's full of mountains and many things. So you get less space for solar harvesting. But for the UAE, right, United Arab Emirates, they basically have vast land to be able to deployed as a solar plants. But then there's also another problem with the water, because if you want to convert solar energy into fuels, another thing that you need is resource, right? And for UAE, they don't have fresh water. Basically, they are located near the sea, so they have sea water, but then they have to use a lot of energy to convert that into fresh water. And creating fresh water from seawater also create environmental impact, because you will generate a lot of brine and then send it down to the ocean, and then the living thing in the ocean might get shocked with the high concentration of salt that this desalination plant releases. So that's one thing you have to know, that sometimes you have more sun, but then you don't have another resource to match, right? But at the same time, if you look at Europe, they have plenty of water, but then there's no space. So this mismatch is something as an engineer you have to understand and try to develop the system that works for certain, climate or certain deployment scenarios. Okay. So after you understand this, I would like to show you this part, this chart. This is the review paper so this review paper is hypothetical, where they want to know if the whole world we want to use hydrogen generated from solar cells matching with electrochemical cells. So use the existing technology. So they visualize that, they simulate the scenario where you need the solar power as the solar panels, and then power the electrochemical cells to make hydrogen. And as you can see here on the top part, if hydrogen is produced solely from the solar energy, you will see that actually the space might not be a big problem, but the water is the problem. If we want to make a lot of hydrogen, you will see here that most of the country near the equators, here the desert, the certain part, like most of China, for example, will have the water scarcity. So you will not have enough water to make hydrogen to supply to the people of the country, right? And that's why, I want to show here that water, and also in some country like, in Europe, for example, they also have the land scarcity. You will see here that, in Europe, there will not be enough land to put enough solar panels to be able to supply, And you might wonder, but what does it mean by 100%, 10%, and 5%? So this is in the assumption that they use, they assume that whatever the space left over from agricultural, from other activities, 100% is used for installing solar plant. So in that scenario, even though most of the country, even that scenario where you use, just the land that we already have, you see that most of the countries still have water scarcity, right? But then if only 10% of the available land is covered with the solar panel, then the problem, you will start to see that, country will have the problem with land scarcity as well. And the bottom part, assuming that the power, what do you have? The power came from wind. So with wind, they also have the same problem, meaning that, not only you see the water scarcity and also land scarcity, you also see, some countries they show both, without water and also land. So you see here that solving one problem, making renewable energy, as I mentioned, require resources and land. And you will see here that, if this is the case, then we have to think how we can reduce this problem when deploying your machine, your solar project into each country, right? In Thailand, you will see here that we pretty much have a lot of solar. You will not see the problem with and we have a lot of clean water, so we don't have any problem. We are in a very good place to deploy such system. But for example, in China or other country, you will not have enough resource. That's why maybe, just maybe, it's an opportunity for us to export our energy to other country, right? So if you see here in the two scenarios, maybe the country that could provide energy or provide hydrogen or provide solar fuels to other country might be Thailand, for example, or, like this part of Africa, for example, or the United States, the North America and South America can be a good energy producer rather than, this country that have suffering from water scarcity, for example. So this is another chart I want you to see. This is UAE, right? It's surrounded by sea, but most of the country basically is a desert. You have, a bit of coastal area where people can live, and the rest is the desert, right? What UAE does, what UAE wanted to put solar project here in this area and supply the energy to the people living in this coastal area, right? And hopefully they can use all this space if they can figure out a way to purify water at a larger scale to supply large scale hydrogen production, then just maybe they can export the hydrogen all around the world instead of oil, right? But I will list down the dilemma here once again, where the country with high solar irradiance usually have lower water resource. And that's true because more sun mean water evaporates more, less water resource. And again, more solar harvesting equal to less space for food and residents, right? So there is a balance, there is a thing that you have to understand when you think about deploying solar project. It doesn't have to be solar fuels, even solar panels, right? But right now in Thailand, we're still far from this discussion because even if we just, because the solar project is only a fraction of the overall energy, supplying to the grid. Right now it's below like about 20%. So we don't have much problem. We can just put, solar project on rooftop or nearby area or wherever there is space. But one day when we want to be more reliant on solar energy, let's say instead of 20% go to 80%, then at that time we have to start to think where we're gonna put it, right? Thailand, we are a bit lucky because we are flat. Thi Lap Lum, we are flat, right? So, and we have a lot of water. So we have that edge against other country like Vietnam, for example, where it's a mountainous country, or Cambodia, where mostly, not Cambodia, Laos, mostly just, mountains, for example. Okay. So this is the chart I drew, and was thinking that, okay, if right now the energy production is concentrated around the urban area, right? Most of the solar energy project is concentrated in the urban area. But let's imagine, what if we go beyond the border of the current border? Where can we go? So I list down 6 areas where we can go. One is water, right? You can float. SCG, they already installed their floating solar farm in many of the dam or their water reservoir. That could be a good idea because floating the solar panel onto the river maybe help reducing, or I'm sorry, floating your solar panel on top of the water reservoir will definitely help reducing the evaporation of the water, right? So you get less water evaporation and people have more water. And at the same time, it helps cool down your solar panels. So that could be a good idea. Another area might be agricultural land, right? You can maybe use agricultural land and build the solar panel on top of your agricultural land to, as I mentioned, sometimes you can harvest both, the light, high energy light for the panels, and then whatever left over the plant can use. And certain plant is very happy with that. And that could be a good idea because, again, the plant, if you put something on top of the plant, maybe it reduces the water evaporation from the plant, and the plant might grow better. So that's another possibility. Forest, maybe a bit difficult. Space, there's also the projects or ideas going around to harvest the solar energy from space, right? If you have the Earth like this, There's no right or wrong, let's just discuss. So let's hear from each of you, starting from Pasta. If you have to, based on your analysis, where would you want to deploy your solar projects?
I think from my analysis, I think farmland is suitable for my solar implementation.
Why?
I think about three things: sun, fresh water, and distance to the city, as well as the transport logistic. So, based on my analysis, I think the farmland is like exposed to the sun enough to create the energy, and then it also have a content of carbon source from maybe from the things that emits there, like from the living things, some organism around that, and they have a fresh water supply as well, and then it depends on how far the farm is. So if, let's say, the farm is near enough, so I think the distance to the city is not the concern, as well as the transport, like logistic. And it also have the high biomass as well.
Good. ต่อครับ
So I chose industrial park. I believe that industrial park has the highest fuel source. Maybe we have fresh water for utilize, and distance to the city is so far, because like if the layoff they can build within the layoff also, but we need to travel to Bangkok, and also biomass. I think there are plenty of biomass in Thailand already, and transport logistics is also good.
Okay, good. Yeah, industrial. You point out something important, because Thailand we have industrial park in Rayong, right? And Rayong is where the petrochemical industry are located. So maybe if we create a monomer, a starting materials, maybe we don't have to go so far to where our off-taker or the factories going to be using that monomers. ชื่ออะไรนะ James how about you?
Well, I would prefer home developers also thinking 10 years there. I mean, it's all of their water, the years there, in there are the slot and also we can use the use of the like in the antenna things wall.
Good. Kiwi.
Also, where industrial. It's has high CO2 emission, so there's a lot of CO2 source already there. Access to fresh water would be easy because it's industrial park, so we can have water for using already. And this I think it's like biomass can be accessed from anywhere, and for industrial park, they will have to transport logistic or any so that's why I don't choose.
Okay, good. You will see that we all, these are the main that we see, and we base our opinion on maybe Thailand or Southeast Asian country, right? So we have a lot of farmland, we have open waters, the dam we have a lot, the river, right? And then the industrial park, we also have, and it's also, if we want to talk about exporting the fuels or the product, maybe industrial park harvesting right at the upstream producer and then transport to different countries may be a good idea. Yeah, and Thailand, we don't have desert, so. Another thing that is quite important is also to harvest right in the city center, right? Right now, we don't have enough technologies apart from solar rooftop to harvest that energy right in the city center. The closer, the better, right? But imagine if one day, I mean, at Gatwick Square, the new building, they have the solar glass. Right? If you go to Gatwick Square, you will see produced by, I think, Asahi Glass, and then they have like a solar panel, semi-transparent solar panel as a decoration, but actually it can harvest energy, actual energy. And many company or many buildings right now, they are trying to incorporate those solar glass into the building, because first it help absorbing the sunlight so people don't get burned inside the building, save the energy cost, and it's also providing more energy for you. So yeah, if you would, in the near term, if you can think of the solution that can harvest, energy in the city center, I think that's the best. We have to use what we have and what is the nearer, the better. And as Pasta said, the microalgae, for example, those, can be harvested anywhere. You can do it on your rooftop. You can do it on, maybe it produce some nutrition or something that you can use. So solar energy basically can be harvested anywhere. It's just where we're gonna do it that make economical sense, right? So that's what we're gonna talk next. Oh, this is the review paper that it just got accepted in Nature Chemical Engineering. So we imagine our solar deployment on the ocean, on the open waters. And this is how it gonna look like in our opinion. So you may have this kind of panels, and then you have the floating platform taking up the water with filtration through the panel and then release it, and then the product get transported to another floating platform where there is a separation and storage unit powered by solar cells. Or you maybe have another kind of device, and as James said, sometimes water is important, right? So we have to use pump to transport the water into the panel, but this another type of device, floating device, you can directly use the water underneath, right, as our resource. So that could be one way, and then we get hydrogen, for example, and then whatever make underneath, we release it, the oxygen we don't need. So one side making oxygen, one side making hydrogen. We keep only hydrogen, and then the oxygen part we just release to the atmosphere, giving oxygen to the ocean. Well, we can also deploy the same thing near the industrial park, where you have concentrated source of CO2. Right now, I just put here the direct air capture machine, but in the industrial park, you have flue gas, for example, you can feed directly into your system, and then you can do the same thing. And the water underneath doesn't have to be clean. Maybe it can be organic rich water from the industry that you need to บำบัดเรียกว่าอะไร condition anyway. So this panel will help conditioning your water pond, in order for you to be able to release to the environment, to the surrounding nature. So yeah, that could be one way. Another way could be, well, this is also hypothetical, producing hydrogen and also water at the same time. So you get two products, water pumping to the city, and then the hydrogen or the gas, you keep it, and then this kind of floating platform, then you can see is if you make this kind of network, the ship can come easily, take out the fuels and then transport it elsewhere. So that could be one way we deployed it. And I want to show this chart because it gives the brief summary very well. So you have when you talk about carbon dioxide cycle, right? You have the carbon dioxide and resources, you capture it, you convert it, make chemicals, make fuels, and then you transport it to the factories to be used, to be utilized, or you can make end-use product like plastic bottle, for example. People use it, and then it turn into carbon dioxide and then go through the cycle again. So that could be one way to think about it. Okay. The next part I want to talk about is the techno-economics part, right? So when you look at the type of fuels that you're going to be producing, you have to look at two things. One is the delta G value, how much energy you need to produce those fuels. And then also the half reaction here, where it tells you the kinetics of that reaction, how hard it is to achieve. If it's hydrogen, it only needs 2 electrons. Very easy, right? Carbon dioxide reduction to CO, very easy, 2 electrons. But if you talk about you want to convert CO2 into ethane, right? C2H6, you need 14 electrons. And you can imagine how complicated that could be, right? So that maybe, these are the two things in terms of thermodynamics and kinetics that you have to consider, right? Maybe making such thing as formic acid, carbon monoxide, or hydrogen, these three are the easiest. But the more complicated stuff, you can see here that 6 electron, 8 electron, when they participate in the reaction, they might do something else, create more products. At the end, most of the time when you talk about CO2 reduction into fuels, you get multiple products. You never get just single product. It's very difficult, right? And that's why you have to think about the separation as well and the transportation. Okay. So if you want to understand the economics of the solar fuels and how we can deploy it, you plot this kind of chart, right? You plot the price at which your product going to be sold, right? So you can see here the price of the hydrogen, how much, the price of the carbon dioxide, how much, right? If you talk about ethane that we just talked now, although it's really difficult to make, but the price is so cheap because right now it's made from fossil fuels, right? It's a byproduct of petrochemical. So it's so cheap. So maybe we don't want to try to produce this, right? And then you have to look at the product capacity as well per year, how much, and see whether the market is already saturated or we can still producing something. For example, formic acid, the market is very small, but maybe we can, then in that case, we can maybe occupy the market and try to start from somewhere, right? And the market size, the potential for growth, those are the things you have to look into. So from out of this information that we listed here, we plot this kind of chart. And as you will see here, it's a chart of the efficiencies against the capital expense of the system. So here, the reason why we plot this is want to know how expensive our panels can be in order to be economically feasible, right? So let's see from the methane. If you want to produce methane, right? If you want to produce methane, and meaning that and you take the price of the methane, which is 0.16 USD per kilogram, you will see here that in order to match that price, you have to have your, right now we try to fix the solar fuel efficiency at 10%. This is, as I said, it's a target value, right? Right now we get 1%, 2%, 3%, but we want to reach, let's say we reach 10%, meaning that the cost of 1 square meter of panels to produce this methane has to be less than $20. Impossible, right? How can you make such complicated device $20? So maybe methane is not the best product for us to start with, right? So what is good? Let's look at C2H6 here, right? The ethane. Again, very similar. The price, because the price is so low, 0.28, right? This is the gray ethane you get from fossil fuels price. So your panel needs to be costing $43 per meter square, right? But let's rethink about this. Let's say we have incentive from the government, right? The government said, no, if you can produce green ethane that has no carbon emission, we fix the price for you at $3 per kilo. So if you go to $3 per kilo, right, $3 per kilo around here, and fix the panel at 10%. If the government subsidize this and make it $3 per kilo, your panel can cost as much as $500 per meter square, which is closer to reality for making the actual device, right? So it's right now we just plot the actual data, the actual value of how much it sells for, but in the future, if you want to go faster to the carbon neutrality and would like this kind of technology to be deployed at a larger scale, the government incentive is very important, right? But let's just look purely. Let's look purely at the current data. You will see here, for example, CH3COOH. What is this? Formic acid, acetic acid, right? You can see here that for this product, it's a little bit more, we have a little bit more leeway for our device cost, because the product itself can be sold at a bit higher price, right? $0.5 per kilo. And therefore, our device can cost as much as 218, which is still expensive. Can you search now how much 1 square meter of solar cell costs? The cost of solar cells per 1 square meter. I mean, solar panel.20,000ใช่ไหม20,000คือกี่ US ดอลลาร์600 700600 700 US ดอลลาร์ right? So you see even solar cells that we already produce for longer time, it still costs about this. So if you take that solar cells as a baseline, you will see that out of this analysis, all of this, we only see that maybe formic acid. Is this called formic? Yeah, formic acid. Formic acid might be the best thing or the best CO2 reduction product to start with, right? Because the market value is rather high. And then also, if you look at formic acid, the production capacity per year is still quite low. So we can use solar fuels and create a real impact by, dominating this market and so easier to penetrate, right? Rather than something that is already concentrated. Okay. Another thing we have to look at apart from this is the separation. You will see here, as I mentioned already, CO2 reduction often yield mixture product. And this chart I showed already last time, you can see that, you get different kind of alcohols, you get hydrogen, you get many things, right? When you deal with the complex reactions. And let's just assume that 100% product efficiency or Faraday efficiency can be achieved. You still have the problem of, let's say your product is a liquid product, right? Or it's a gas. Let's say it's a gas first. You will have your product with mixture at the end with water vapor, unreacted CO2, and supporting electrolyte and many things, right? Or even if you make formic acid, which is in dissolved in liquid phase, you will have also formic acid dissolved together with other salt, electrolytes, and formic acid is very good at forming azeotrope or hydrogen bonding with other things inside the water, so it's very hard to remove. So yeah, that's another challenge that we have to think, like how we can separate our product, and not many people talk about it, right? So I guess moving forward in the future, not only we have to try to make our production of certain product more efficient, but we also have to look at the way to the best is to not separate any product, so to use as is. For example, if you have mixture of CO2 derived product, and you can use that to burn or to do something as is, where you don't have to separate the product. That may be the best, right? Because separation can sometimes cost even more than the energy itself to make the product. So yeah, there are hidden costs for separation and transport, and this is when you design your system, or when we discuss about deploying the system, you have to discuss all these things: market value, market size, system cost, energy requirements for making the product separation, transportation. And this is the chart. I just try to make the star chart for understanding a bit more about the potential of each CO2 derived product. You can see here formic acid. Among all this formic acid, we have the highest allowable system cost. So how expensive we can use our panel. We can use to produce our panel. So, and then the kinetics is also easy, right? The product separation is a bit hard, but manageable. And then the market size is quite small, so it has a lot of potential for growth as well. So that's why in this paper, we recommend formic acid as our number one near-term product to aim for. Okay, that's the end of my class, and this is the first homework. So in this course, we will have around three homeworks, and this is one of them. And I would like you to discuss and write a report about the scenario where imagine we install the solar fuels plant in Pak Isan, right, where we have a lot of sun, but maybe less. We have a lot of sun space, but less water, right? And then we want to transport that to the SCG Chemical to in Rayong to be produced, to be converted or processed further to make green polyethylene, right? The plastics, right? So yeah, discuss about the fuel type that you choose. So you have to see first of all, you have to see what monomer, what product out of this can be converted to polyethylene, can be converted to ethylene, right? And which product makes sense, right? And then discuss the challenge of production in Pak Isan and then the transport, Yeah, so it's just a 1 to 2 page report. You can submit it on 28th of October before midnight on my course view. Yeah. Okay. Any question about the homework? So just 1 or 2 page is enough, and you can put some pictures or whatever you want to show for your discussion. Okay, and the problem-based group projects that we're gonna be doing. So who is going to be with who and what project are you choosing?